2 weeks ago, I think, I present this one to like I have one model. It's polycetylene. So that one is single oligomer. So from that uh, model, I did the coupling that calculation, and using the coupling calculation, from that coupling calculation, and lots of file, we coupling file in energy pop and that MATLAB code, we did the RR calculation, and we plot this kind of graph. This one actually the previous I did, and now professor told me to do that. And for the electronic dynamics calculation, actually first we need to change the initial condition. So we need to be carefully select the value of the initial electron values for HOMO, and it's a yeah. Professor, if I say anything wrong, please correct me. And for the LUMO, yeah, we need to select the some values, and for this calculation we need obviously we need input overlap, energy pop, and the RR value of the previous one, and for master optics this one, and band out, um, and using this files we will able to calculate the electronic dynamics things using the shared code by professor. So this code are obviously provided by professor, and these values homo lum and the minimum values of the model is 64. It's for my model, and mm, like here I think this one is the most important for plotting the those graph already showed by Amir. And so like here I choose the 5. That means for homo it's like initial homo -4, and this one is so this one is homo -4 and lumo +4. It will show in this graph for this. And here we are able to see the inner energy time versus energy graph. So and this one is for the lumo. uh, Professor, am I right? It's a lumo, right? Yeah. So it's so when we are plotting and those graph, it shows that from lumo +4, its energy is increasing around 2.2. Then when time increases, it's not time increases, time decreases with the decrease of time, because it's a logarithmic scale at time, and energy is like drop from lumo +4 to lumo +3, then lumo +2, lumo +1, then lumo, and it's goes to like shows the energy in when it shows in a lumo condition, energy around 1 electron volt. For the HOMO, because HOMO is a HOMO -4, so HOMO -4, for HOMO -4, our energy, the value of energy is less than obviously HOMO +4, and we can see that when time it's around 1, it's energy started to like goes up, and the HOMO position, it's the line shows, their line shows the straight line. Oh, sorry, straight line. So here energy is -1. So we can see from here that in relaxation time, like if we compare for HOMO and LUMO, this one, the yellow line shows the LUMO and the blue line is HOMO. So if we compare these two, then HOMO needs less time to relax the system. So this one actually the result for the in a z direction position only for the electronic state. That means in a HOMO position, I don't have enough uh, knowledge for the explanation this one. So this one shows the electronics, not electronic state. So, it's for the position for in a z direction for the holes, and because I choose LUMO HOMO -4, yeah, LUMO +4 here. So from that it's shows some peak here, and because if it's a 3D picture, if we I can't move here, but if we rotate in this position, how to in if I able to rotate in this direction, it will shows the particle inbox like the sine wave. This one uh, this one actually is the margin of the, it's like the values of electrons and holes, HOMO and LUMO. It shows in the 3D direction. On it shows only the z position in z direction. So it also shows the how they relax the system, but it the electron and holes together. The yellow line one for the holes, yellow line for the LUMO, and the blue lines for the HOMO. And this one, I think this one and the first figure is the most important figure for this plotting. Like here, we are able to see the inner when we did this calculation, energy for this HOMO +4, yeah, HOMO +4, its peak is so high. In its intensity increases with when in actually I found. Professor, can you help me to explain this one? Yeah, you are mute.
There will be dedicated speaker number 6. David will explain it in details, but maybe, David, would you like to help right now to Keya, just to interpret what she computed?
These are intensity graphs. You're looking at a time integrated of something. I'm assuming position of electron based on what you just showed us.
Transition energy.
Or, okay, time integrated the transition energy, that makes sense as well. So the last graph, I can't read the numbers on the one on the internet was something like 100 picometers. That was your time range on it. So this just condenses that all, and you get a nice time integrated graph. Does that make sense?
Yeah, a little bit. Okay. So for the electronic state, like I choose 5, IE5. So that means HOMO plus electron, HOMO minus 4. So that HOMO minus 4, that in that state.
So I'm assuming there's a 4.5
4.5
EV excitation there.
Yes. So it seems like that this one for the HOMO minus 4 excitation energy for the HOMO minus 4, this one. Then it shows the other values like HOMO minus 3, then HOMO minus 2, like that, if I'm not wrong. Then HOMO minus 1, then HOMO. I think so. Like this way. It shows the excitation energy for that one. So like in intensity high, then low, then again -4, -3, -2, then HOMO. Then in the LUMO, it's excitation energy again like 1.5. I don't know about this, why it's like a straight. It's excitation energy. This one also shows the excitation energy, but why all are goes to infinity, I don't know. I don't get this graph, like why it shows straight and it seems like that it goes to infinity. But if I said that okay, it's for HOMO minus 4, in that state it shows the higher excitation energy, like 4.5. But why here it's like this kind of shape, and it's why in the second graph, in the this one, second and this one, it's a different shape. I don't get this. That's what there is something I don't get time, or I don't have. I need to spend more time on this.
Keya,
Yeah, hi.
can I
Hi.
ask what's the difference in the x-axis between the two figures?
Yeah, it's a logarithmic scale and it's a normal scale.
Mm-hmm. So how do the like relative intensities compare? Or like on your right figure, the highest x value is like 0.3,
Mm-hmm.
whereas what would be like if you converted the x-axis on your log scale into regular units?
It's x-axis is normal scale, in both. Only sorry, x-axis in, and there is a log in figure 1 and figure 2 normal scale.
Mm-hmm.
So you want to say that because of the change of the scale, that's why it shows the different kind of figure shape of this figure.
Mm-hmm. Like if you just made your x-axis bigger, it might make more sense so that you can see the ends of all the peaks.
Yes, here. Yeah. Okay, I got it. I understand. Okay. Thank you. Yeah. There are several graphs. Then obviously in this kind of graph there are several excitation energy graph plot this one in the logarithm scale but z direction. So it's from my observation, what I understand that the figure I showed this one. This one actually showed in the different position, right, Professor? This one,
Different time.
different time, and in obviously position is changed, like we showed in 3D level in a different uh, direction, like different position. Sorry, z position, z x here z. There's few other plots here. This one, this for me it's quite difficult for understanding. This one, I don't get the. It's
Let's leave it for the discussion by last but not least speaker. So David will probably cover it. Or David, would you like to briefly tell what it is right now, so that we all follow what is going on?
You're looking at the excitation dynamics. So where the excitation is in time, it's a lot easier to visualize if you lay it flat instead of seeing the peaks and just compare the colors.
Yeah, thank you.
At about 10 picoseconds, it looks like it starts decreasing in energy, give or take.
like there. It's
Yeah, pretty much.
in this here.
Yeah, so the one on the x-axis equates to 10 picoseconds.
Yeah. So this there it's like decreasing.
Yeah. So the big peak that you see at the beginning is your initial excitation, and then it decreases until the band edge, assuming you don't have any intraband interactions, which I don't honestly know what your model you're looking at.
Okay, yeah, thank you, David.
And this one is the last figure.
Skip this one. It's you do not
okay.
need this one.
Last figure, then that
Okay.
is the last figure.
Then please join me thanking Keya. So any questions are very welcome, and I see there is at least one typed in the chat line. So for next three speakers, I'm asking to scroll back what was delivered by first two speakers and analyze what is missed or seems misunderstood, so that next speakers try to add systematic foundations. And the first two speakers basically show what should be highlighted and on what which we should focus to make everyone to feel comfortable and understand the procedure. So there is a question by Mead, and Mead, would you like to verbalize your question if your microphone is working, or you want me to speak it out? So Mead is asking probably about, oh, okay. And while preparing for the next presentation, Aaron, when Keya will be done and you will be starting speaking, maybe you can share link to your example files in the chat line. so that everyone who wants can take them as an example.
Dr. Kine, may I have a question
Yes, please.
from you or related to David answered that question? So to choose the right value for IE and I forget IH. So I choose 1 and 1. So
1 and 1, it is a trivial. It will show 2 parallel lines. One
so
for HOMO and 1 for LUMO. So
you suggested based on oscillator strength, right? For instance, the first peak of the transition energy that you were talking about. If that's the case, so I expected to have that peak at the energy level between HOMO and LUMO. So I'm getting something wrong, or
no. Are you Mid? Are you connected?
Yeah, I'm here. Yep.
So we'll finish with Amir and then get to your question. Okay, would you please share a screen and go to slide about 3 or 4 at the where you have energy relaxation?
Yeah, just a minute.
I think it is oh, not 4, maybe 11.
Yeah, just 1 minute. This one?
Go back substantially.
Okay.
Back. Stop here.
This one is the first figure.
So let me answer to Amir. So you see on the left side there is a screenshot of the command window with 2 numbers. So these 2 numbers show the slope of the solid and dash line. And these numbers will be different for each initial excitation. In a narrow sense, the productive stage of calculation is to scan through all possible pairs of IE and IH and find out how the rates KE and KH depend on those pair of excitations. So how the specifics of excitation affects specifics of relaxation. So single run is not sufficient. One needs to run it again and again with different values of IE and IH and see if it changes anything in the dynamics. Make sense?
Yes. So how find the so we don't want to put this independent plot for each pair of the orbitals. So
if you are thinking about publishing, you show only the most representative figure.
So what is the most representative? This is the question.
You will see it. You will see it when you get to it. But believe me. But to represent 100 other runs, you just collect the data and plot them as like dependence of this KE and KH as function of excitation energy.
Okay.
Summarize many data. Let's go to a question by Mid. Mid, would you please verbalize your question?
Yeah, it was actually shown on the next slide.
Next slide?
Yeah. So, like, for example, you have position Z in angstrom, right? And, you know, the way I'm thinking of this, and please correct me if I'm wrong, I'm thinking of, like, electron density throughout the molecule when I'm seeing, like, position and intensity. But I know there's a time interval as well. So this is the excitation energy throughout the molecule changing with time and position. Is that right?
Yes.
Okay.
Anyone wants to add to the discussion? Oh, let me try. So, Mid, there is a big lie of quantum mechanics that in postulates of quantum mechanics, there is a statement that quantum system prepared in the eigenstate will stay there forever. And this is correct only mathematically. In real life, any excited state will relax to the ground state, right?
Okay.
So In context of this figure, the leftmost distribution corresponds to initial state, rightmost distribution corresponds to final state. And it shows this principle that system goes from excited to the ground or lower in energy state. So charge density changes over time because energy is dissipating from the system.
Okay, thank you for clarifying.
Does that answer your question?
Yes, it did. Thank you.
Okay, yeah, thank you. There is a question from Sean. Sean, would you like to verbalize your question? Okay, not a problem. I'll read it. So Sean is asking, should IE and IH be the same value? I would think the most significant pair would rarely be the same. Maybe David can share his experience on this question.
In my experience, I would tend to agree, but it does happen.
So, Sean, I think the demonstration that is represented now is only a single run that shows proof of concept. To get scientifically important, valuable results, one needs to rerun it again and again with different pairs, and of course, non-coinciding IE and IH would be among them.